stations and 3 phases. So if you feel that it's difficult to understand every point here, it's okay. So the examination will just focus on the basic knowledges, right? I will not ask you just to calculate the very difficult problems. Very difficult questions. So you do not need to recite a lot of the equations. You do not need to explain to calculate very complex conditions. Not necessary. Okay. Or if you would prefer some challenging tasks, it's okay. Please tell me. Okay, let's get started with the teasers, right? Yeah, so, and this is the voltage and the current range. Yeah, but in the time domain, because there are 2 domains, the time domain and the phase domains, right? So, this is the time domains and the max amplitudes of the voltage and the current, and with the functions, let's do this sinusoidal or cosine functions like this. So this is the time domain, the voltage and the current will be the instantaneous expressions. Okay, so you can just to write down the important part usually, because GPT I will send it to the group chat, and also the textbook. If you have some programs, you can just do searching on book is okay. So you can learn from this, the omega. The omega, so is the angular frequency, right? The omega is calculated by the double the pi, the multiplied with the pi and the frequencies, right? The frequencies in China is 50 hertz, right?
Standard frequency.
Yeah, so it will be a constant value if you are using the equations within here. So these 2 are the max amplitude. Here, yeah, this is the max voltage, the amplitudes of the voltage and power range. And this theta is the angular offset. Yeah. If like this, we form the offset will be 0, right? But doing like this or doing like this, yeah, we can do that maybe 60 degree or minus 60 degree, right? Yeah, this is the theta. The theta is just to offset the angular. Yeah, you know this. That's why
different of phase.
Yeah, different of phase. That's why we have the 3 phase, power. Of course, we will discuss in the later part. This part of this lecture. So, and you know, so this is not a constant or the constant value, numeric values, and will be rechanged over the time. So we will just use the mean, root mean squares, the RMS of the voltage, right? The root mean square, you can just to view it as the average of the current or the voltage. Because why we do not just to divide it by 2? Because the root mean square is the effective value of this waveform. So we make like this. Like this, we're just doing like this, right? Because we only focus on the energy or only on the power value. So we can use the rho mean squares. This means these areas and these areas will be the same, right? So the rho mean square but we also record its effective value. So, how much power that this current source or what source will produce use this RMS, right? Square 2 multiplied with the amplitudes of the voltage. Okay. Just like this. We assume that it's 1 volt and this is 2 volt. Okay. So there's the adders and additives. Do you know this?
Yes, sir. Yes, sir. I know this. This imaginary content real part complex.
Yes, it's just to convert the form of the expressions, form of the voltages and our currents into the other forms. Let's use this to write down. We write down this one to this. That's why we call this the angular of these waveforms, because it just to convert these cosine functions that here.
Leading or leading angle.
Yeah, leading or the negative, not negative. The angles here is mainly focused on the leading or the not leading. So
this leading, this current is fast.
yeah, if the angles here is positive, is
yeah. So this is the leading.
No, you are not sure that if this angle is negative, so
the lagging.
negative.
If this one is the unity.
Okay, so you mean the complex phase, the matrix consists of the complex phase consists of 2 aspects. So first one is the magnitude is here, right? The absolute value of the voltage, or you can see the largest one, or the RMS square, right? The effective voltage is here, and the angle is here, right? This is the two main points of the complex phase. Okay. Okay, you can just have a general understanding. It's okay. You don't need to know every step of how this line comes from. So let's recommend. Yeah, this is the 4 formations, and this is it's a 10 years the waveforms, right? This is effectively voltage, the current, and you can just to convert this angle to these 2.
Yes, sir.
Right? Because the errors identities divided by 2 parts, the cosine and sine and this imaginary part and the real part.
Real part? It's complex number.
In the power system, I can just give you some definitions. This is active power, passive power. And this active power is corresponding to the real part, right? The passive power is corresponds to the imaginary part. Why there is a major case here is because the passive power does not make sense in producing power, in producing energies, right?
So this is the imaginary part.
Yeah. So the waveform sine functions corresponds to the passive, right? Because it does not make energy effort, right? Okay, so
only this energy is active power.
have to know there are three main devices: resistors, inductors, and capacitors. Right? 电阻、电感、电容。Could you imagine this?
Yes. Impedance.
This is the resistor. Yeah, of course, if you are in the United States, you're doing
This one.
yes, it's both forms
The
of
same.
the same thing. And in
Inductor.
inductor,
Coil.
it's doing like this.
Capacitor. Equal sign.
Yeah.
Impedance is resistor and imaginary of inductance. Real.
Yeah, so you can see that the impedance is these voltages in these three devices in the time domain actually is much more difficult. So this class, our former name of this class is steady state analysis of our system. We are not going to learn the transient state. And if you are learn the transient states, you are using this.
This electric circuit theory.
Transient states analysis is much more difficult.
Chapter 6.
Much difficult. So you can just use this one, the figure, right? It's quite easier. The voltage, I, and the current and the resistors, right? Inductance and this capacitors is the value of this inductor and capacitors. The omega is, you can see the 2 double the pi and that pi and multiplied with the frequencies, right? This is the omega, right? So you have to use these phasor calculations to calculate the voltage. This is the relationship between the voltage and the current. Okay, so you see the resistance and reactance is also that the power that is in the same form, the resistors, the reactance, while this one, if we consider these two, we'll get the impedance Z, right? That we make. The R, the real part is the resistor, right? The imaginary part is the reactance. So generally, so the resistance will be resistors and the reactance will be inductor or the capacitors. Or you can just do M two in this, because this two does not make the effort, make the powers directly, right? Because let's say this two is on the imaginary part.
Capacitor is integral circuit. Capacitor is integral differential.
Yeah.
Resistance is differential.
Yeah, that's okay. And it's the different interpretations. So yeah, of course you can use this angular forms. Z is the amplitude of Z, right? The mass of this, and this is figure of this angle. So for two is okay. So Z is quite easy, right? This is rectangular. So you can calculate this using these two, but you have to use these figures in everything. You have to it's easier to understand and calculate the value. I will give you one example, okay? And the current source, right? And this is the resistors, it's the American way resistors, 4 ohm, right? And this is inductors, 7 point almost 8 milliamp. So this is the voltage, the good source to produce. So you can just use this write down in the angular form, right? Angular form or in the base domain. And frequencies is 16 hertz. This is the American. You can use it in the American for system. And the resistor is 4 ohm. The reactance you can just do
Omega 2 pi f. Omega equal to pi f. Omega equal 2 pi frequency.
Yeah, 2 watt per with 3.1 per and
Frequency.
not per with 60 and per with 7.96
96 into 10
Right.
minus 3.
Yeah, it's, you can just get the reactance is 3 and the resistance is 4, so that 3, 4, and 5 that this is a very general numerical value of the rectangular triangle. So the angle where you can use your calculators is definitely so this will be first handy, right?
Yes, sir. This is 3.00085.
Yeah, this one I need to use the calculators.
The number.
The current, right? Current when you just do image the voltage
Divided
divide
by
the
impedance.
impedance. So the real number is just do 100 divided by 520, right? The angular you use the minus, right? Okay.
That is complex version.
Yes. Angular you use the 30 degrees minus 30 and the 6.9 degrees. So it will be minus 69, right? So the multiplier for the angular is a multiplication, or is a plus or add just A and B. If you like to calculate the multiplication, and if you wish to calculate the divisions, this minus and minus, right? The angle Y minus the angle B is here.
Is also same.
Yes, it's okay. ID. And you can also just write it in the time domain. Right? This is the RMS value, and this is the angular piece of this. So this is the instantaneous power. So we grab the voltage and the current in the time domain. This is power, right? Voltage, current. This is right down in the closed functions. So also you can use the sinusoid functions. It's also okay.
This is the log.
So this is
The ruler property.
ruler properties of.
Yeah.
If you know it, it's okay. If you do not know it, you can just do it that, well, this power is equal to this. It's okay. You do not need to understand the average mathematical steps. Some of them will be some difficult or not frequently used, because for me, maybe I have learned this in my school, or so it will be more than 10 years ago. So for me, I even do not remember how this property is here.
We can also use this one. Cos omega plus t plus theta b cos omega t cos omega t minus sin omega t.
Oh, yeah.
These two is same.
You have very good skills in mathematics. Okay, so for these properties, I think if we are not, if this is not a major, we are not a major in mathematics, you can search or online when you use it. You do not need to remember or research. Okay.
But this is the basic of this trigonometry.
Yes. But if you have used it frequently, you can just use H, write down H, use the screen. So it's okay. But I mean, so you do not need to
Take the question.
the same H maybe read H 10 times or 30 times to remember this. I think it's not necessary to do so.
But this property is very important in EE, engineering electrical.
Yes, then you can just to graduate more and then you will keep it but not in your hand. So we'll just to here describe instantaneous power. So the set the average, right? this is us actually, so we just to calculate the average of these two. Just to get the sum, of these two average terms, right, variant terms, and then we can just to get this one. So in this part, you can just have a look at it because this is in transition. It's related to the transition stage estimation. So it will not be included in our results. So just have a look at this and knowing, oh, this is the instantaneous power, it is where it is in the time domain, okay? Power factor. Okay, so
Power factor in the phi.
yeah.
There is a factor also.
Power factors just like this two. You can either right, this one. So this is the power factors. CF, right? Just that the difference between these two angles. Okay? Power factors?
Yeah.
Angles.
The line. Line.
So you can import in that countries? Okay. And so we're doing like this gradations of the famous powers. Not even this part, because first you have to look at the non-equations. So okay, so this is an important part. We are learning about the complex power.
Reactive cost, real power. SQS.
S is
Complex
power. So it's also the complex powers can be divided into two parts, the real part and the imaginary part, right? So P, the real power it's also used like this, the P, real power, the Q, reactive power does not mix any realities. So, okay, so please pay attention that the units of the two is not different. The watt, kilowatt, megawatt, kilowatt, and megawatt, yeah. So this is the different units for these two.
The complex power is VA, kVA, MVA. Complex power is VA, kVA, MVA.
Yeah.
Volt ampere, kilovolt ampere, megavolt ampere.
Because the complex power is from the voltage and the current. Yeah. So this one is quite easy to understand.
Voltage and
var and SME.
So voltage, ampere, what the meaning of what?
So it's actually we know that the power factor is anger. So the power factor is the power factor is anger to that power factor anger, and you can use this. This is a function that is anger. So this is the power factor's anger, and this is a complex power, like the reactive power, real power, and the reactive powers. Or you can just say this the active with the passive. It's okay. You both the same things. So and power factors and use at the leading and lagging, right?
Yeah.
If the current leads the voltage, this is the leading, and if the current lags the voltage, it's the negative. So it depends on the factors in the positive negative factor. Everyone reflected your
CIT. Oh, CBIT. I know that, CBIT. The current, control current voltage.
No, okay, we can
I have this, I remember this.
So, if you do not know about this one, you can just use this.
CIV and VIT.
Yeah, this is the capacitors, right? Capacitor. And this inductor.
Inductor. Capacitor, inductor, voltage current.
So, for capacitors, the current is
Voltage.
leading the voltage, right?
Yes.
For the inductors,
Voltage,
is
current.
the current is lagging the voltage.
Okay.
Okay, it's okay. It was this okay. So you can just remember this word. So it's easy. So the capacitors, for the current is leading, the inductors, the voltage lagging. Voltage is leading, the current is lagging. Yeah, it's okay. It's both the same way. It's a few expressions for the same thing.
See with this famous rule.
Yeah, it means that if you have the complex power, you are destabilized.
You need to do something realize. I
Yeah.
remember this one.
Okay, so this is the triangular I have to write down. So yeah, that's easy, right? This is the complex power. This is the real power. This is the active power. And this is the angle between the complex and the real power. Right, so everything you can get to get from every aspect equation, you can get to calculate or just to directly get from this triangle. The PS is the power factors, the complex power, right? Okay, so everybody understand this? It's pretty easy, right?
Lagging.
Yes, this is the calculation method for this. You can just use this triangle, and you can just do this is the cosine, right? This is sine,
Yes.
and this is the numbers of this triangle. Cosine, sine, and so the examples. So node 100 kilowatt and leading power factors 0.85. So
This is the negative.
I heard you there. So it's quite easy, right? Because you have these triangles. Triangles, you do not need to recite or remember all of these. Just like this. These equations, you do not properties equations, you do not
This is the middle.
yeah, you use the angle, yeah. And for this, you can use the calculator to do this. And also, please remember that the pay attention to there's whether positive or negative. Yeah. When the power factors is leading or negative, so please pay attention. So the minus.
The minus. This is the lagging.
So consumers, so then you can get to get the reactive power. Can I say it?
Yes, sir.
Yeah. Minus 62 kilowatt. Kilowatt just means that the load is consumers. So we consume the 62 kilowatt. We consume the positive. So that's why the load is negative here. So the capacity, right?
use the reactive power.
So I will give you an introduction about conservations here. So, okay, for this three, we call it the node or bus, right? And this is the connection line or transmission line. So this is the basic system. Okay. So and it means in every bus or node, it is the A, B, C in these three. Sum of the real power in the node is B equal to 0. So why? So can you explain this for me? So why the real power in the node should be equal to 0?
If this real part is 0, this energy is not transferred.
Yeah, so it's actually you have learned the PCL and the KVL, right? Yeah,
That's a parallel and voltage law.
because everything, because if we start not equal to 0, so our energy balance theory will not reduce anymore because some energy is lost here in my
This will not exist.
yeah, you can see there's per P post. Okay, so the Russian's name is very difficult to read. The TCL, right? Okay, so I'll give you examples on this. And this means the angle is 30 degrees, right? Basically. And this here is resistors with 4 ohm, and this is the inductors 3 ohm, and here is the J, right?
Yeah, this is the
This is
imaginary.
J. Right?
This inductor, so this is the imaginary. Okay.
So in the previous examples, that the current is that value, right? So current here, we have to take an image for this. So you can also use these equations, use all of these triangles just to calculate all of these necessary parts of this circuit, right? The complex powers, right? Here, voltage here, because this is a new voltage source is that here, and current is here, current because in this is calculated in previous examples here. So of course you can see that the real the numeric part is set to like current 220, my current is 100, it resulted that the angular is set to 830 and 0.9, right? And you can use your calculators
I can do some
to convert it to the
real part and imaginary part. Let's calculation.
yes,
Real part and
it's
imaginary
actually, I think it's actually the
600.
approximate
part.
value.
1600.
Because actually it should be 37,
Yeah.
7 degrees.
I got the resolution. So 2000 is 1600.
But here's one thing here. So in the power systems, because we are supporting the large networks, very high value numeric values. So we in most cases we do not need to get the exact numbers. Just the approximation or estimation is okay. So using the 36.9 or 33, it's both
It's okay.
Yeah, we are not doing the power electronics. And they are more straightforward. Okay, so the error is the power factors. We can also calculate this. The cosine, right? Cosine this.
This, yes, cos inverse.
So the complex power of the resistors, right? And this is the part A because the resistor is 4 ohm, right? The current is here. But why the current for this is positive 60 point? Anybody knows this? So why here is the positive and here is the positive and or negative and
one is imaginary current and one is real current. This I is this one is real current, this I is imaginary, so this is the minus.
Yes, because we are calculating the resistors. So this one is to get the voltage, right? Voltage, and then we have to use this, the current of this for the circuit. So that's why here we use the minus angle, right? For this. So the current will just to get going through from these resistors, right? So can you understand this? Why the I with this 10 stars and the upper row and this current is different? So have you understand this one? Okay, so the powers of these resistors, right? It's pretty easy. We can use because this is current, micro and current. So no matter the negative or positive, the total value, the absolute value will be the positive. So here you can see that the resistors, the angle is 0, right? Like this for resistors. So that's why we have this word CVOT. Only the capacitors and inductors will produce the reactive power. So resistors is okay. So resistors every power will make effort. So the angle is 0 here.
So this is 60.
But you see that the inductors
make it logic.
Inductors in this circuit is okay because this two current is, you can see the compensate, this angle is compensate for this one. So in this situation, the current, the angle of this inductors is 0. So in this circuit, the inductors do not make any reactive power or passive power. Okay, so as you see, this is no. This inductor does not make any active power or the real part.
Only has this reactive power.
We would say that this inductor is here just to waste some with all the energies because it does not make any efforts here. You think the real part, the positive, the active power is here is 0, right?
Yes, this real power is 0, active power.
This one is equal to 0, but here is J, right? This means all these are on the imaginary part. And here, right? 0, this angle is 0, right? So in this situation, the resistors make all the effort, make all the power. However, the inductors do not make any real powers here. So, but the inductors account for the whole imaginary part, or account for the whole reactive power. It's okay? Is there any?
This, so that the 200 VA.
But you have the I, right? You have the I, so
I is VA.
yeah. So that's why in some cases, maybe for the inductors, maybe they do like this, right? In this case, so the reactive power is here a lot of reactive power, but in that case, the inductors will also make some active power. So when the angle is not equal to 0. Okay? So, but in this case, the inductors do not make the active powers here.
Like this. This is resistor. This is 6.9. This minus 6.9.
So then, I think I'm going to step to put it in 0 back because this is the multiplication. Then this angle is A by this angle. So it's 0.
6.9 minus 6.9.
Yeah. So for the resistors, they do not have the magnetic part, right? So all we need is the active power. But for the inductors, the order part is magnetic part. Yeah,
but they have no active power.
Yeah.
So all the active power.
Yeah. So so the capacitors or the inductors generally may produce the reactive power.
Not active power.
Not active power. You can say that the active power or the real power is 0.
But for this resistor have this reactive power is 0. And the DL is 0, that means P real power is 0.
Yeah.
This have no real power is 0.
Yeah, you can say that why this bar, right, with the watt, different is
this one is imaginary, one is real.
And in some cases, if we add the resistor, the capacitor, and inductor in the same situation, so that's why we produce that angular were not equal to 0, right? In some cases, that's why the PC, RCL, we call it the RCL situation or
RCL.
Yeah, it depends on your demand because maybe I will need some active power or I will need some reactive power. So reactive power, it does not mean that it's useless, okay? So it does not make it may not produce the power directly, but in some cases the reactive power is also important to maintain the operation or the rule of the current, okay? So reactive power does not mean it's useless. In some cases, we will even create some capacitors or the inductor to raise or increase the reactive power.
I made the example.
Yeah. Very nice. When these two angles is not equal, wow, then this angle is the angle of the whole situation will not be 0, right? Because it says this is P, this is L, and this is the chord is not going to be 0. Right? Even in this situation, right? In this example, the resistors, the inductors, and they will produce
This is a real part.
and the angle is 37 degree.
This is the lagging.
Mm.
This leg.
So of course it's a lagging, right?
Like this.
Because the phi is more than
Yeah, thank you.
it's positive.
And for this example, where this 100 and 260 and 40 and 84.
Yeah. Of course. In different approach with different numerical values, you can just use the exact same because this is the example. No measuring what the resistors, how large the resistor is or the inductors is. So the calculation method is the same. Okay. Okay, so if I will send this to you, and if you will need some practice, you can do this. It's okay? So this angular and this angle, the positive 60 and 69 and the negative 60.9 will be 0. So in that case, the resistors and the inductors will have no angular. So the resistors only produce the active power. The inductor here only provides the reactive power. Okay. And power consumptions. Yeah. So here is the summary of these three types of the devices, right? That's why the resistors were only the real power, the inductors only consume the reactive powers. Because you see that this is a positive, right? A regulation. The negative means the power is generated, but the positive means the consumed, right? So that's why the capacitors is generate reactive powers. The capacitors and the inductors, and we know the symbol, right? So one is lagging, one is leading. So this two is generally in the very opposite position or the opposite functions.
Yes.
So one is generation, one is consumers. So at your demands, you can just to use the different inductors or capacitors in your circuit. So the calculation is doing like this: capacitors, the inductors is just not. Inductors is computed by the multiplication, but the capacitors is related by the division. Given this, this is the 5, right?
Plus J40.
J40, right? And this is the 100.
So this total is 105 plus J40.
And this is 40,000 with 0 degree the voltage source, right? Because this voltage negative like this.
Okay, again try.
So the current is pretty easy, right? Because there is no angles, and all the angles is 0. But the voltage is not different. Yeah, voltage, you know that. This is 40,000, right? 5 multiplied by 400 is 2,000, right? So this is the real part. and by the imaginary part, the 40 multiplied by 400, because there is no degree, the angle is no equal to 0 degree, so the 16,000 in imaginary part. So just to divide it into the two steps. First, calculate the real part. Next, you can just to calculate the imaginary part. And this, you can just use the calculators. So the complex power direction is also System-2. So the complex is 44.9 kilo. Do not forget the 1000, okay? 1000 multiply this, and you make this. This is megawatt, right? Megawatt, watt, yeah, megawatt. And for the answer is the answer 220.8 plus 0 is considered this one. Yes. Okay, you understand it? Yes, that's right. Okay? Okay, so I easily okay, so do some more, so another node that reactive power node, and this is the inductor, okay, so it's 100 in the 100 in the imaginary part, okay. It's okay. So is okay. So next get some new instructions about communication, right? First, yeah, the one-line diagram. One-line diagram means that we just use this one single line to drive the whole system, right? Just like the previous situation, right? And this is the generator. Generator, you can just do showing like this or other forms, so it's okay. It's American ways.
This is the bus line.
Yeah, this is the bus line, and this is the two devices right here. And it's showing that the voltage levels, because there's the higher voltage levels, and this voltage levels will go from high to low. Right? This diagram in software. So this is used in your software, right? But of course, that's different directions, and it's actually more frequently used in the software. So this does not overtake this in the location, because in the handwriting or in the book, I think it's not easily understand more than the
But only software simulation, you need to understand.
Okay.
এইটাই তো পরীক্ষা হলে এত সমাজ হলো আরে শেষ করে দেবো সমাজ 240 উঁচু বাকি তাহলে আপনি অনুযায়ী জমা করতে হবে তো
আমি কিছু বলছি বলতে বলছি
হতে পারে একটা ইলেকশন দিয়ে হবে
তাহলে আমি দেখি কেন
আচ্ছা এর আগে এর আগে 100 দিয়ে বাদ করছিলাম
তাহলে এখানে তোদের আগে দেখে এগুলো করে রাখি যা
Any questions? Okay. Any questions? So, how to do like this, the reactive compensation.
দেখবেন কিছু দেখ উঁচু দশটি তো নাম করলাম নাও তো বুঝলাম ইন্ট্রোডিউশন this is the parallel
Okay.
এটা ভোল্টেজ যেটা রেজিস্ট্যান্সে বাড়তেছে কারেন্ট বাড়তেছে ফাইন্ড দিস কারেন্ট
impedance, right?
Right, yeah.
But impedance we use 100 on the 100. Right.
define this current
Yes, I know.
Because the current is equal to this is the voltage, this is the resistor, right?
We use 100.
Yeah. What 100?
Yeah.
The same. Oh, it's here. If here, we don't use this 5. Yeah,
We did not use.
We don't only use 100.
this is the real
I think that this is the fault, the errors here. This is to be the resistor, and here should be the inductor or whatever. But for this, that you can just focus on the numbers because this you do not just say you can look like the imaginary part, right?
you just find the real power
Yeah, this is the error. It is the error of the calculations. But here should be resistors.
but this is the like saying in the
Doctor,
this will be inductor, this is the resistor
Okay.
because this is the ohm and you have to find the real power so you divide it 100
Yeah, of course. Well, I think that you're very doing a good job. I do not think notice that. In the American way, the resistors and inductors is a little bit similar.
different in the resistor is like this and inductor is like this
Yeah.
this is the two this resistor this is inductor
So this may be something confusing or similar.
yes
Okay, so I'm sure because what is the reactive compensations? Yeah, if this circuit, it means that we have to add more reactive compensations as the node here, right? In the case that the reactive compensations is necessary, so do you know why there is a parallel connection between these two? Why do not keep put these capacitors in series connections?
because sir we know this capacitor
You have heard this, right? You have this.
when this
Mm-hmm.
if we give like this series
Mm-hmm.
this is our power this is capacitor this is the power this capacitor take a big amount of power so we can get this enough power and if we give this the capacitor is we can take our enough power and extra power take this capacitor so that's why we give this parallel if we give series we can take enough power
Yeah, exactly. Estimate.
Thank
So,
you, sir.
and this is the summary. Yeah, it's quite simple. If you would prefer to calculate the capacitors, in the parallel connections, C1, C2, C is equal to C1
Plus C2?
Yeah, the parallel of capacitors. However, for the inductors,
L1 plus L2
Okay?
Yes.
So this I think it's very convenient for you to understand capacitors, because capacitor, you know, it's the E, it should be the 1 divided by the J and omega and the capacitor that is in the lower part of this function, these divisions. So if you doing like this, because the L is the multiplication and the capacitors is the noise on the divisions. And this is, you can just do, remember this one is more easier. So if you would like to compensate some more reactive powers, so just to sketch a parallel connection of the extra capacitors. Okay?
And when C1, C2, C
I will make some instructions for the function of the reactive power. Okay, so as I said, the reactive power does not mean the useless power. This is some functions of this, right? So the reactive compensations where can decrease the line flow, can just to reduce the line flow of the from here to here, right? In some of our daily operations, the transmission line or the transmission line has this constraint, right? Maybe this transmission line is only affordable for 500 amperes, right? But if we have to operate of this transmission network, we can just add some reactive powers. Now, you can see. Doing like this, right? The mass angle, right? In that case, right? The mass flow, the current can be reduced. So we can just use why the reactive power has its own functions or place or its own rules in our power transmission networks. Doing like this, we can just use a different angle. You want more voltage, but of course in that case the voltage is higher, right? So in some cases we'll need smaller power range, or some other cases we'll need the higher power range but smaller voltages, right? So everything you can just design for your own design, right? So the current is can north down, the 9 losses can also decrease. It's very important, right? Also, the north orange can use the smaller wires. The smaller wires, the smaller the wire is, the cheaper you have to pay for this wire, right? So the voltage drop, if first you know the voltage drop can also be reduced. So why the reactive power? So why we need the inductor and capacitors if the reactive power is useless at all? So why should we just to design to invent these two devices, right? So that reactive compensations, so it's actually used frequently and widely in our power transmissions and work. Okay.
I think maybe without capacitor, our forward will be damaged. Just to use the capacitor in high transmission line and our forward.
Doesn't have this maybe. So why is some upper transmission lines and screen noise, right? Give some, or this person doing this. This is a switch, and you can just do parallel one or improve the efficiencies of the overall power transmission. So that's why the reactive power is also functional. Our factors corrections. Okay, so let's see the example, and you do not need to calculate this. Okay, so this is a situation voltage. This is a 100 kilowatt load with leading power factors, right? We would like to try to the power factors. Okay, you can just to and you can just to reconvert this. This is the angular form of the power, complex power, right? 100 and with the angular flash, you can just convert this. It's okay? Yeah, 60, 80, and 100 is the angular flash angular flash. And you can get the angular is 33, about 33. Okay. No, 37. Okay, so 37 degrees. Okay, so you can also then just calculate the 0.95 the TF request the angle in the base
18.2.
So the new complex power you need is doing like this, right? Because you need some compensations. Then let's calculate this, right? Let's make this angular part here, right? Understand?
Yes.
Yeah. Just to compare the new complex power and the original complex power, the angular right, and I think it's kind of easy. So if you feel that this equation is maybe confusing or difficult to understand, you can just draw two triangular wedge. One is for the original, one is for the new. Wedge is much more understandable. And so this is the capacitors. Well, here just to get a power balance with this.
High voltage
Capacitors, yeah, it's for the reactive power compensation. Yeah,
Now, so why we use capacitor this line?
This is something like
Yes.
it.
Why we use capacitor in this line?
capacitors, yeah, because yeah, you see, the thing like this, the capacitors is used for compensate the reactive power. So actually, active power is the energy we need, but reactive power, and as you can see, yeah, I think we can get to summarize the function of reactive power is help you to get down the loss, get down your cost for the power transmission, right? Although we can also transmission the same amount of energies, however, we can just to lower down your loss, right? You can just to pay less for the same amount of the output. Okay? So it's okay. So I was saying this CBT. Yeah, your chat.
ক্যাপাসিটার মানে ট্রানজিট যেমন আমাদের যে কোনো জিনিসে রান্না বান্না করে কি আমাদের হেল্প করে যে হয় না ক্যাপাসিটার এরকম হেল্প করে আর কি একটা ভালো উপযোগী না।
Okay, so three phase systems, we will have to have this next week. Okay, so I will take 10 minutes. Will take 10 minutes for you to just to make a. Have you learned about this one? No.
Delta, why delta?
You have know this or
No, no.
you do not.
forgot last week.
No, if you do not know this, we can just to have learn this next week because there will be more sufficient time. Okay. So this week I will give you an introduction of the smart grid.
You can give introduction for next week.
Huh?
For next week, you can give introduction.
Okay, so you can choose we can just to finish the three-phase system or you want to finish this one?
Yes, this three phase.
Three-phase? Oh, okay, yeah, it's okay.
Only the display voltages.
Okay, so that's okay, fine. We can just go ahead. Okay, so the balance. So we have to learn about the balance three-phase systems, correct? Yeah, three volt sources. Yeah. Okay?
Yes, okay.
So this is three phase. The balance means that every voltage, every phase of voltage is the same, like A, B, and C. Okay, so if you were in American, these guys will be X, Y, Z. Is okay, the same. Like this, 60 degree, 1 and 20 degree, okay. It's A, B, C, like.
There is a 360 divided 3 phase 1 to 3.
Yeah. This is the that. But ensure that the amplitudes of the voltage is equal. Yeah, same thing.
Same idea.
Yeah, equal loads, equal amplitude, impedance on the line current on lines. Okay, so be sure the average thing in each phase is the same. Okay. Large power system, so the three-phase system is almost everywhere in our power systems. Single phase is doing like this. It's very low voltage, low power settings. So even the distribution line never tempers to be three phase. Right? Okay, you can see. Okay, so there is no transmission. But you see the transmission lines in our campus is also three phase. But in our room, it's single phase. Single transmission used in Europe. Okay, so I'm not. It's out of my range. I'm not. That's the place. And so okay. So this connection is we call it the Y connection.
Yeah. Why did
In
you
Chinese, 星星, the star, right? And also there is a delta where we call it the 三角形, the delta. Okay, so this is the this is the single, this is Y three-phase systems, right? So you can see the three voltage sources, three nodes, right? They're all equal to the Z, absolutely the identical impedance, right? This is the single system. So this is a zero neutral current. We call it the neutral current. So when neutral, you can see the neutral point of these three phases equals the neutral point of N. And when this current is zero, right? Zero, and according to the KCL rules, A, B, C, the current, the sum of these three phase current to be zero, right? When this is zero. So the neutral current is zero. So the complex power of all the three phases, that's 2, 8, 3, exactly. Okay. Of course, the voltage in the Y direction is here to here. Okay. So make sure that the voltage on each phase is just to covering the source or covering the nodes, right? Here, here, here.
This is the rule why
And this is delta, right?
this delta this y.
This is
When I
y.
convert to the y, so R1 equal
Oh, okay. So you have a really good memory because this questions. And the Dodge, maybe I could also think I will remember this questions now. Okay, so it's the advantages. The first thing you can just do need more powers, right? Because we have 3 lines. You cannot just to transmit as same as a single line. Because we can see it here, right? Three times. Even though there might be some reactive powers, but more is generally more than twice as much as single lines. So the port is also constant, so fluctuations might be reduced. The fluctuations in the waveform or the current is more steady, right? 3-phase machines use mass materials. Okay, so I'm not familiar with this one. Okay, the fourth one is 3-phase machines start easily than the single-phase machines. So, okay, so if you guys, some of you guys in the future work in generations, just tell me why about this one.
I will say.
I'm not sure how to start this, but the generators, if you would like to start a generators, it's actually very tough and expensive work.
I understand what you mean. How can let's explain? This is A, A. This is B, B, C, C. This is 3 phase, and this is 1 phase A, A. So this is our stator, this is our rotor.
Yeah.
So physically it's also easy to single phase because this rotor is plus minus plus minus plus minus plus minus. At the same time when I give
Three times the force, yeah, 3 times the push, right?
this pushing this side, pushing, and this pushing this side. This is S pole and pole.
Yes.
So this will be powerful.
The total one is here for this, right?
But single phase, this only give is this is this only is this and this flashes come down here. This two.
Much more, the larger, the higher parts.
The higher torque.
Right.
And this speed is going is milliseconds is going up so powerful. Like a bullet train or metro, this using this kind of machine.
Perfect.
You see, like this only 50 seconds, 60-second bullet train.
But it's for machine, but if you were in the plant, the very large generator is not more difficult. Because maybe 4 or 7 years ago, one starts there tells me that in combustion generators, if you voltage one time is the cost you maybe 300,000. Yeah, one time.
300,000
Yeah, 300,000. Yeah,
one time.
one time. Yeah, or it's almost 2 to 3 hours. Why? Because it's too large. Like you cannot just fill into the tiny generators or tiny bottles.
This is a big.
Okay. So we have to accelerate the Y and the cross, right?
Yes.
And this is the Y connections. The yeah. One is 110 degrees, 91 Okay, so it's very easy to
This is
understand.
I can write the AM equal the
Yeah. And this is the source of voltage, right? And so the vector expressions of this. When you would like to calculate the voltage between the two interfaces, then this is the VAN, right? And this is the VEN, but EN is because this is directions, is different directions, like EN is from here to here, right? So here we should just to reverse the directions to the opposite directions. And then this, so this is the VAN minus DEN, back EN. Then we got this VAD. Okay, so VAD you can just say that because this is a piece, the angle of this is 30 degrees. Okay, so this plus this for this edge.
We can also write this as this is BN, AM, CM. So AM uses 90 degree, 90 plus 30 degree.
Yeah, 90
So,
minus there.
90 plus, this is our one. So this, we know this is the 90 and this is 30. So 90 plus 30 will be
120.
120. And then BN, this is this is BN. So we know this is 180
Minus
180 plus 30. So this is 240 minus 20. So B
minus or 24, 240. Is it okay? It's okay. It's okay. It's okay. But you can calculate doing like this, right? So this is the voltage between the two faces, right? Just calculate like this. So the wire connections